session is over, it's over, and yeah. And when that happens, then I have to go back and go over the lesson again by myself, which is kind of tough. But the last property we're seeing in, let me make sure, yeah, I had covered this the last time we met. The last property we're seeing in solution is the existence of osmotic pressure. So before we get into what this pressure is, we're talking about osmosis itself. So if you've taken a biology class, you have talked about osmosis versus diffusion. Diffusion tends to talk about the flow of molecules. Usually it's covered in the context of gases, and you have gases flowing from one area to the other. In general, so I can remove this dart here. In general, molecules tend to flow. So right here, in general, molecules flow from an area of high concentration the term gradient is sometimes used to low concentration. Okay, and this usually happens naturally without the help of the scientists. Things tend to move from a higher gradient to a lower gradient. It can be a concentration gradient or a pressure gradient. Gradient just usually means there's some kind of difference in whatever unit was mentioned before. So it can be a pressure gradient, it can be a temperature gradient, a concentration gradient. So it flows down from the high to the low. And this happens naturally. Okay, so the context here is we're looking at a difference in concentration. With that being the case, usually diffusion and osmosis are studied at the same time. With diffusion, it's very obvious when we're looking at molecules of gas. Gases will move from an area where you have a high gas concentration to an area where you have a low gas concentration. But when it came to osmosis, the definition was, this one was a little tricky for me at first until I realized what was going on. They say here it is the flow of solvent from a solution of low concentration into a solution of high concentration. So up until this point, when I learned about osmosis, all the flows I had learned about before were from high to low, from high to low. And I said, with chemistry and even in biology, certain observations tend to be very familiar. So I've heard from high to low to high to low. So when I got to concentration, when it was being introduced, I expected from high to low. But when the teacher said it, she said from low to high, and I was like, what? Wait, now we're kind of flipping our observation. Why are we looking at it from low to high? So, I mean, she kept talking, and I'm obsessed with this concept here. I'm stuck. Why did we flip it? Why are we not focusing on the flip and everything? Anyway, so in my own private time, in my own private reading, I had to make a sense. I had to make sense of this switch. Why are we suddenly seeing a natural flow? Because this happens naturally against the concentration gradient. It didn't make sense. So in statements like this, you want to really examine that, the way it's written. We're told osmosis is the flow of the solvent. So the solvent is a liquid like the water, which is moving from a solution of low concentration into a solution of high concentration. So if you're anything like me, that flip will bother you, which it did, and my teacher never addressed it. Okay, so let's look at what low concentration versus high concentration looks like. Okay, remember, we're being told the movement this time is from low to high, which is opposite to what we're expecting, right? Low to high concentration. And so here's the thing. In the end, what they were saying was what I was expecting. They were just saying it differently than what I would have expected. In a low concentration solution versus a high concentration solution, I will use the red circles to represent the molecules of the solvent. So remember, what's moving here is the solvent, right? And we are used to, once again, molecules, chemicals, whatever, bodies moving from high to low. So if you have a low concentration, the implication here is you have solvent. And so I'll keep the solvent amount fixed, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, On the right, same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If it's a low concentration, this usually talks about the solute in the solvent. So after I sat down and examined this, because I was obsessing over the definition, I couldn't get over it. I realized, oh, low concentration technically, relatively means you have a few solute particles. Okay, so the solute particles here are few. That's what low concentration means. And then high concentration, here you have a whole lot of solute particles. Many solute particles. Okay? But the thing that's moving is not the solute, it's actually the solvent. So when the teacher was communicating, and as I was reading this, once again, with chemistry, there's certain parts where you want to slow down and make sure you really understand it. The thing that's moving is the solvent, not the solute. So that tells you, and the picture I have here is so-so. I like their picture a lot better, because in their picture here, they show you the solute particles. The solute particles can be salt, it can be sugar, whatever it is. Let's call that sugar. So on the left of this tube, the U-shaped tube, you have two compartments separated by a semi-permeable membrane. The semi-permeable, semi means partial, right? It has holes in it, and the holes allow certain molecules through, but doesn't allow certain molecules through. So it sorts for certain molecules against other molecules. The molecules that are able to pass through here is water. So water, our solvent, is able to flow, can pass through the pores. The pores, okay? So it's semi-permeable or semi-porous, allowing certain molecules through while it disallows certain other molecules through. So if you look at this picture here, if you were to count, because their picture is a lot better than mine, if you were to count, you can see there is way more water molecules on the right. So we have a greater concentration of water molecules compared to the left. In the left, you have lower water molecules. So when they said that the water molecules was moving from a place that had a low concentration, in the picture they have here, way better than mine, the part that has water only on the right technically has no solute, so you can say this is relatively low concentration. The part on the left that has solute molecules and water will then have high concentration. Okay, so with that being the case, what is moving? Water. Where is water moving from? It's moving from a side that has a low concentration, which is a side that also has a lot of water, to the side that has very little water. So in the end, we're talking about a movement from high to low. The terminology they used focused on, in my opinion, the wrong thing. They didn't say the flow of water is from the high concentration of water to low concentration of water. They said it's from low concentration, meaning of solute, to high concentration of solute. Okay? So that terminology does matter. They weren't necessarily communicating something that was unnatural. It was still from high to low, but the wording is focusing on the solute versus the solvent. Okay, so why is all that important? This movement is important because we start off with a natural flow from an area that has a lot of water molecules to an area that has less water molecules, right? From left to right. You can see here they're showing you a natural flow in the beginning. There is more water molecules leaving the right side, going to the left side, right? As you can see, shown by the two arrows here, versus a few of the water molecules, once they get to the left side, go back to the right side. So one arrow versus two arrow. Well, what happens after a while? After a while, the water level on the left side, since most of the water molecules on the right, move to the left. After a while, you have a lot more water molecules on the left side than you did on the right. So just in case you're trying to see the big picture here, in the beginning, both water levels were similar. Okay? The water levels are being drawn to the area where there's less water levels or water molecules. Eventually, Now we have so much water in here, so much water, that solution has become more dilute that the water in here starts to push back. Okay, there is too many water molecules. Now the water molecules start to push back. So that back pressure that prevents any new additional water molecules from coming in to the left is what is called osmotic pressure. I can't spell right now. Let me tell you, when I was a student, I had to read this part a lot to get it because for me, the concept of osmosis was not intuitive. There's certain areas, where you just kind of feel like it's not really meshing or jiving with who you are. That's okay. Just spend more effort to get it, right? I had to spend a lot of effort to get this part here because I was like, this is not really intuitive. Like, I get it, but it took me a while, right? So, yeah, molecules of water, the only ones allowed to pass through the border, are able to go through. But once they get there, the very water molecules mixed with the solute, either salt or whatever, begin to exert a pressure that prevents any additional new molecules from going through. But the arrow is indicating here molecules are still traveling, right? But here's the clincher or the idea. Any new molecule that moves in here gets replaced by a molecule that moves out there. So now you have dynamic equilibrium, right? When you have one move here, another one moves there. So overall, there's no change. And the amount of water molecules on both sides remain constant. Okay, so you can say if you do a census, you count the molecules on the left of water, that amount remains constant. So the pressure that makes the water concentration constant in the solution pocket is that osmotic pressure. So hopefully I've explained that. Once again, it was one of those things that took me a while to really grasp, but that's the osmotic pressure. So it shows you once again the solutions are separated by a semi-permeable membrane. Your body is full of these semi-permeable membranes, allowing certain molecules to go through, certain molecules to not go through. So when I was in school learning this, some parts, especially in chemistry and in biology, some parts of it, I'll get a little bored because there's no math, no mystery to solve. So it will remind me of my youth, right? When you went to places that maybe they serve alcohol or something, they don't just allow you to go in. The bouncer at the door, I'm talking about, like a club or something, they'll be like, show me your ID. So in my head, as I was learning this, I saw the semi-permeable membrane as the bouncer saying, well, if you don't have the right ID or something, you can't go through. So the solute particle can't go through, but the water particle gets to flow through and go back and forth in and out as needed because they have the right, in this case, structure, right? So your body has a bunch of semi-permeable membranes that allow certain molecules with certain characteristics to go through, other ones can't go through. And sometimes these membranes protect organs and things like that. Anyway, once again, this allows the solvent to go through, but not the solute. So the amount of pressure needed to keep an osmotic flow from taking place is called the osmotic pressure. Those water molecules that were able to go through, enough of them went through to where they're like, okay, now we got enough pressure here. They start to push back. So once you understand that, now we're going to the math part because our goal is we're trying to figure out the effect of the solute on the solvent because the solute is present. We now have an osmotic pressure. Now, this is the thing I realized about chemists, right? When I was learning chemistry at first, it was a little tough for me because it was hard for me to imagine myself as part of the process. But after a while, I started to think about the chemists, what they were thinking, and then me as part of the process, and it made things a little bit easier. Remember in 1411, we had the Pervnert equation, the ideal gas law equation, right? PV is equal to nRT. We talked about the gas pressure. That was the pressure here. But now we're dealing with another pressure, only the context here is not a gas. It's osmosis happening inside a solution. So how do you distinguish this pressure from the gas pressure, P gas? Well, we now have pi in the place of P. And over here, just to see how the relationship works between these two, if you take V and divide, oops, I had the wrong thing on. If you divide V on both sides of the equation, this cancels out. You get P equal N over V RT. N over V, I'll just work it on the side here. N over V is essentially moles over volume in liters. Moles over liters. We learned that, right, before, and we said that's essentially molarity. So moles over liters is molarity. Remember, in this context, we replace P with pi. So that's how we end up with this equation right here. So this equation is somewhat a different form, just a rearranged form of the Perv-Nernst equation or the ideal gas law equation. Okay. As we did with the ideal gas law, pick an R value that works for you. I like this R value. In chemistry, when I was going to school, my teacher, whose background was in physical chemistry, he would give us like 4 different R's. And then he would just kind of mix it up without any logic or any reason. Today we're using the one with bars in it. And I'm looking at him like, can we stick with one? You know, I was one of those people, you know. And then after a while, I decided to pick one that I liked since that wasn't happening, and this R was my favorite one. So I would suggest that this is the most popular one used in this context, even in ideal gas laws. I would say this is a safe bet. So why is selecting the correct R important? Because it helps you to modify the units of the other measurements to make sure that everything works out as far as dimensional analysis is concerned. Our R is 0.082, I'll just say 1, this part here. You can use that if you want. Liters times atmospheres over mole times K. So we're trying to make sure all of our other measurements have the units that are compatible, right? So we can cancel things out and make sure dimensional analysis works. Okay, so we got the R unit out of the way. Based on this, the temperature unit has to be in Kelvin. So for this equation to work out, make sure temperature is some number with a unit Kelvin so that they can reconcile right here, right? And then moving on, so we've gotten R, we've gotten temperature. Now N over V, that's molarity, right? The molarity part, molarity, remember, is moles over liters. That has to be moles over liters. Can we find moles over liters here in the R? Yeah, it's just flipped, right? Liters over moles, but that's the inverse of molarity right there. What else? Oh, one last thing, ATM. Okay, for this equation to work, you want to remember, so we've gotten that, we've gotten this part. Your pressure has to be in ATM. So regardless of the units they give you, use the molar gas constant as an anchor to make sure that all your other units reconcile. Then everything will work out, right? So your pressure has to be an ATM, so that when you do that, pressure has to be some number, unit ATM, so the units can reconcile here and here. Now all the units reconcile and your math should work out correctly, right? I remember taking physics classes and chemistry classes where I had the equation, right? And I put in the numbers and I swore I did it right and I still got it wrong. I really hadn't grasped the concept of dimension analysis. Your units have to be right, okay? So here's the practice problem. We're told the osmotic pressure of a solution containing 5.87 milligrams of an unknown protein, okay? I guess we have the information here. Let me copy that. But I'm going to read through what I'm copying just to make sure. Okay, so I have the mass of the protein written down here. I'm assuming the solute, so I'm going to write here, this is my solute, right? Milligram of the protein per 10 milliliters of solution. This is the volume of solution. Okay, you are also given the osmotic pressure of the solution at a particular temperature. Oh, it was given here. I'm like, where's the number? And asked to find the molar mass of the unknown protein. Okay, so my pressure is in torr, right? So this is pressure of the solution. And this is in torr. And temperature is given to me at 25 degrees Celsius, temperature of solution. Okay, I know the equation I use is the modified ideal gas law equation, pi equal m r t. I know that pi has to be in atmospheres, right, per ideal gas constant units. So I'm going to write this here. The ideal gas constant is going to be 0.0821 liters times atmospheres, which until I memorized this, I called it Latin and then mole. Because I was okay, so I have some lazy tendencies and I didn't want to pull out the book all the time and flip to the back and find this list. So I'm like, I'm tired of flipping all those pages, flipping pages. So I'm like, I'm going to memorize this so I don't have to figure out what the units are all the time. Yeah. So you have that right there. Pressure has to be in atmospheres. Big M is better if it's in moles per liter, right? R is the units we got here. Temperature has to be in Kelvin. Okay, so I can go through and start converting, right? So let's see. What I'm solving for, what is the wanted again? Oh, find the molar mass. So I need to have that here so I know what I'm looking for. What is wanted is some number. Molar mass has a unit of grams per mole. So when I get my answer to have the unit grams over moles, that's the molar mass, right? So all my math is going to make sure that I end up with grams over moles. And when the units is right, my assumption will be the number is right. Okay. So let's see. The pressure is here. I have R, I have T. That means what I'm trying to solve for, the molar mass, is hidden somewhere in here, right? So we're going to start. Pi is equal to mRT. Once again, remember I have these numbers. That means whatever I'm solving for is somewhere in here. So I'll start by solving for M, the molarity. I'll rearrange this equation first before I try to solve anything. I was told by my students they prefer I do it that way. So I was like, yes, ma'am, and yes, sir. Okay. So I'm going to put the M as the subject. I'm just flipping this over. Equal pi over RT. Let me see. I feel like my table is a little lower. Okay, that's better. So right here, oh, my units are not my desired, yeah, my numbers are not the desired units. So I have here pi is 2.45 torr. Now you want to have that pressure conversion, right? Remember in the pressure conversion, 1 atmosphere is 760 torr. So I need to convert this. 1 atmosphere, 760 torr. Because remember, in dimension analysis, the units have to match diagonally across, right? 1411. Yeah, it's coming back. Okay, let's see. So I have 2.45 torr. Let me make sure I'm using the right number. Divide by 760. And I end up with 0.00322 atm. So I finally have my pressure in the right unit. I'm done with that part. Molarity, I'm going to solve for that first before I start rearranging things. And then R is in the right unit. It always shows up in the right unit. Temperature has to be in Kelvin. So I now have temperature at 25 degrees Celsius, right? To change to Kelvin, I have to add 273.15. And that gives me Kelvin. 25 plus 273.15. I get 298.15 Kelvin. Okay, so I finally have the right units. Now I can finally plug in the numbers, right? I call that prepping your numbers, kind of like when you're cooking, you're prepping your ingredients to have the right flavor. My numbers are prepped, so now I can put them in here. 0.03, I left it 0. 0.00322 atm over R, 0.0821 liters times atmospheres over mole times K times 298.15 K. Okay, and I have my units here to kind of assure me along the way. I like assurances. ATM cancel out, K cancel out. Liters over mole, right? The denominator, When it goes to the denominator, it pretty much flips over. So the mole will now be on top and the liter will be on bottom. Oh, that's a confirmation of what I'm doing because that is the unit for molarity. Now I got to do my math. So for my math, I'm going to type in my 0.00322 and take that number divided by 0.0821 and then divide it again because I'm dividing it by all my denominator numbers. My calculator, y'all, is such that I have to do it that way for my calculator to do the right calculation. I divide by everything in the denominator. So I have 0.00013, I round it up as 2, okay? So here, let me just verify before I continue. Yeah, they're going to be doing that. They're kind of going about this that way. Okay. Okay. So you just want to check. So here we are. Now that we have our molar mass, they said we have to get what? Grams over mole. That's what we want to have. We want to have our unit to read grams over mole. Now I have moles over liters. So I'm not there yet, obviously, right? So I keep going. I know molarity is equal to moles over liter, right? You can write the moles with the ES or just like that. Moles over liters. Moles of solute over liter of solution. Let me see. Do I have a volume here? Oh, they gave me the volume, but the volume is given to me in milliliters. Well, that's good. So looking at the numbers I have right here, let me do a quick inventory. I have molarity, it's up here. I have liters, well, not liters yet, but I have milliliters. I can convert it. That means I can solve for what the moles are. Okay, good. So volume was given to me as 10.0 milliliters. And now I want to convert volume to liters, right? 1 liter is 10,000, not 10, I should call it 1,000 milliliters, right? So to convert the 10 milliliters to liters, I'm just going to write 10.0 milliliters. I do my conversion brackets. 1 liter, 1,000 milliliters. This cancels out. It ends up being 10 divided by 1,000. And I have 0.01 liters, right? So I finally have my volume in the right unit, which is 0.01 liter in the liter unit. And now I can go ahead and multiply that by molarity to get moles. So to solve for moles, I'm going to multiply M times L. That will give me moles. So moles will be equal to molarity times liters, right? So molarity is going to be what? The number I have up here, 0.000132 mol over liter, right? This number here and the units times the volume I have down here, 0.01 liters. When I multiply that, my answer should be in moles, and the units will be in moles because the liters cancel out. The unit is correct, so it is worth doing the math, right? Oh, I just erased my last number. Let me see if I can press answer and see. Oh, it's okay. Okay, so I have my number. I'm going to multiply 0.000132, and these are 3 zeros. Let me make sure. Yeah, 132 times 0.01. And I end up with so many zeros. 0.00000. 1, 2, 3, 4, 5. 1, 3, 2. Or you could write this scientifically. I'll say here, or 1, 2, 3, 4, 5, 6. 1.32 times 10 power negative 6 moles. My calculator is set up in standard notation, not scientific. So I have that. Okay, so we want to figure out the molar mass. Molar mass is essentially mass in grams over moles in mole, right? So if you have your mass, divide by the moles. We just got moles right here. So I have this. Let me go check and see if I have grams. If I have grams, I just have to divide it to get molar mass. Let me see. I think they gave me grams somewhere here. Oh, are you kidding me? They gave me grams, but it's a milligram unit. Okay. Let me not be lazy. 5.87. I can do that conversion. I was like on a roll. So the mass was not given to us in grams. The mass is 5.87 milligrams. Let me verify this. Oh my goodness. They wanted to make sure you converted everything, right? Okay, we need the mass in grams because that's what was it's gonna fit here. Okay, so 1 gram is equal to 1,000 milligrams, right? So 5.87 milligrams, we're going to convert this to grams, 1 gram on top, 1,000 milligrams on the bottom. Yeah, wow, this is one of those questions where you're converting everything. So you see how when I was still trying to figure out how to solve these problems, I'll just plug in the numbers. I'm like, okay, I got all the numbers I need. I'll just plug away and then get the wrong answer and be very upset. 5.87 divided by 1,000 because dimension analysis is very important. So our grams here is 0.00587 grams. Finally have the mass in the correct unit to place in here. Okay, so mass has to be in grams. 0.00587 grams divided by moles has to be in moles. 0.00000 5 zeros, 132 moles. Okay, this is finally the right unit, right? Grams over moles. Let's see if this works out. This is our molar mass. I write it like that. So we got the top number, 0.00587 divided by 0.123. So I'm actually writing the zeros. So 1, 2, 3, 4, 5. So 5 zeros, 132. Okay, so my molar mass ends up being 4.447 grams per mole. Okay, this is weird. Let's see what they have for their answer. Now, their answer, I guess they did round it up to 3 significant figures. So if I do mine the same way, I'll end up with this stays, this stays, but then the 7 gets converted to 0. So 7 is bigger than 5. Bigger than 5. You want to round up. So it ends up being 4.450 for 3 significant figures, grams per mole. You can write it this way, or scientifically, you can write it as 4.45 times 10 power 1, 2, 3, 3 grams per mole. I think they have theirs. I think I saw that was scientific notation, right? Yeah, scientific notation. So you can write it either way. Of course, if you're working on a multiple choice exam and the answer is provided to you, if it's scientific notation, convert your answer to their answer so everything matches. Does anybody have any questions? So you see how the molar gas constant played a very important role, right? So that wasn't explained to me that way when I was learning it, but I was like, why? Yeah, I figured the correlation there. So I usually tell you guys, the constant they give you is very important. Use the units. If you leave the units out, you can think you're doing the right thing, but there's no way of confirming it, right? Because you don't have units to cancel out to know you're doing the right thing. So you want to do that. Man, they converted within the calculation. You can do that too if you want. That just sounds risky to me. Okay, so in the dialogue of your pre-lab, they did refer to Van 't Hoff factors. So what exactly is Van 't Hoff? Van 't Hoff actually contributed to the modified ideal gas law in 1411, the permanent equation, the one that had all the other stuff. Him and van der Waals contributed to stuff, right? In this context here, Van 't Hoff noticed that ionic compounds produce an even greater effect. So if you're trying to compare, so I'll say here in the comparison of solutes, comma, all solutes are not alike. Oh, now I can't even spell the word alike. It has one L. Okay, alike, right there. They're different. Apparently, ionic compounds, because ionic compounds can ionize, they produce multiple solute particles by ionizing, right? For each formula unit, then they kind of just ended it there. So they talk about it down here, but I want to complete that statement here. I want to add to it here. So ionic compounds produce multiple solid particles for each formula unit. What does that mean? Ionic compounds produce a heightened colligative property. So whatever effect you have, property, whatever effect you have, the effect becomes stronger or more experienced or more visible if you pick an ionic compound over a molecular compound, right? Because in the beginning, when we're talking about the definition of uh, colligative properties, if you're ever wondering why the definition was so vague, it was because of this instant right here. The definition of colligative property was it was a property experienced in solution whose effect was based on the number of particles present, not on the type of particles. What kind of example is that? But in the context here, they were defining colligative properties based on this context here. If your compound that you put in the solvent can generate more particles, that compound will give a heightened effect. So what do I mean by that? Before we come back to this slide here, let's take a little detour. On a cold day like today, I think about colligative property. It hasn't snowed yet. Let's look at sugar. I'll actually look at glucose. C6H12O6 versus sodium chloride. These are both compounds. The one on the right is ionic. The one on the left is molecular. Okay, so you have these two. Okay, when you add these to water in different containers, so they're not in the same container, right? In different containers, what do we see? We see that as far as the molecule is concerned, you go from having solid sugar or solid glucose to dissolved glucose, which has the same chemical formula, just a different symbol. Okay, so this one here on the right is I should say, dissolved in water. Okay, and this is what happens to molecular compounds. So we're having glucose represent molecular compounds, right? Versus what happens to ionic compounds. Remember, ionic compounds ionize. And don't forget, ionic compounds are the ones that are majority made up of metal and non-metal. What do they do in water? Well, we're using sodium chloride. Sodium chloride starts off being one particle as a compound, solid. You put it in water and it ionizes to form two ions, sodium ion, aqueous, plus chloride ion, aqueous. So since the colligative property has to do with number of particles, not identity, doesn't care about whether they're molecular or ionic, just cares about the number of particles. I'm going to count particles. On the left, we have one particle. Particle is a generic term that can be molecule, atom, ion, whatever. So one particle. On the right here, we still have one particle. Okay? Here, though, an ionic compound, we start off with one particle. On the right, we have two particles, right? When they dissolve in water. So from here, according to Van Hoff's factor, if you use the same amount of table salt to make a solution versus the same amount of table salt to make of sugar to make a solution, you will have twice the colligative property effect in the ionic compound, aka table salt, because you have twice the number of particles made. It doesn't matter whether the particles are smaller or bigger or ions or whatever, you just have twice the particles, you have twice the effect. So here I can say doubles the effect, or kind of intensifies it, right? Effect. Okay, let me kind of continue a little bit more. If sodium chloride doubles the effect, what does calcium chloride do? calcium chloride ionizes to form calcium ion plus 2 chloride ions, right? So you look at this and you started off with 1 particle. Now you end up with how many? 3 particles. So guess what? 3 times the effect. Thrice? I don't want to write that word. So I'm going to say 3 times. 3 times the effect. Okay? And if you can get another compound that has 4 of the other ions, or even if you have 2 and 3, once again, as long as the ionic compound can ionize to produce whatever you're looking at, let me see. Yeah, it will essentially, the number of particles multiplies the effect. Okay? So remember, ionic particles multiply the effect. So when you're solving problems, just in case you were solving problems in your homework, and they gave you ionic compounds, you want to pause, right? People tell me I read slow. I'm like, yeah, when you do chemistry a lot and that's your major and you have to read slow because you're constantly asking yourself, is the conversation about a molecular compound, ionic compound? Is it ions? Is it compounds? Is it elements? And all that stuff, it slows you down because you're constantly second guessing yourself or questioning what you're doing, right? So what I mean by that is when you're giving formulas, you want to be aware what type of formula you have. So here we're told non-electrolyte. This is one that does not ionize, right? Does not ionize, aka molecular compounds. So the question could use the term a molecular compound. They could give you a molecular compound, or they could just be lazy and say non-electrolyte. So they don't even tell you what the compound is. They just say non-electrolyte. So the context here is you, for whatever amount of compound you have the exact same amount in solution. Okay? So this table here is communicating something. The Van Hoff factor I is a symbol used to represent. This represents I should write the word. Number of particles in solution. Okay? So if you examine it real quick here, we end up having twice the number of particles. From magnesium to sulfate, we have twice the number of particles. Magnesium chloride, 3 times the number of particles. Potassium sulfate, 2 potassiums, 1 sulfate, right? So we have 3 particles. Iron, 3 chloride, we have 4 particles, right? So this is what we expect, the enhanced effect. We should have 1 times the original, double, double, triple, triple, quadruple, okay? So what is the expected versus measured? Whenever they say expected versus measured or versus actual, we're talking about lab versus what we expect theoretically. So theoretically, based on Van Hoff's conclusions in his experiments, this is the number we expect to multiply our colligative property by. But if you go to the lab to try to prove what Van Hoff said, sometimes you don't get the actual numbers. So they're saying here, if you go to the lab to try to produce the factor by which your colligative property is multiplied, you most likely get 1.9 versus 2. Here you get 1.3 versus 2, 2.7, 2.6, and 3.4 versus the numbers on the left. So why is there a slight difference on the actual part of the experiment versus the number provided? There's something called ion pairing. If your solution is not dilute enough, so for concentrated solutions or non-dilute solutions, something called ion pairing happens. So these ions, they separated when they got in the solution, right? As is the nature of ionic compounds. But because the concentration is so high, these ions, even though you see how they're being surrounded by these water molecules, this process is called solvating, okay? I have a picture in my head, and I'm going to share the picture. You know, we probably may think I'm a little special. That's fine. I think about this kind of like parents. They used to be together. I mean, they're still together, okay? They're still together, but they got a lot of kids, and the kids are like hovering over them, mommy, mommy. Anyway, yeah, the kid around here, not kid, kids surrounding the parents, and they're kind of hindering the parents from getting together. But the parents are kind of close together. If the concentration is very high, even though each ion is surrounded by water molecules, they're still able, due to high concentration, get together. Because if this can't get to that, since you have many other chloride ions or sodium ions, they can get together with another ion because the solute concentration is high. When this happens, it reduces the Van 't Hoff factor, so it's not ideal, just FYI. So, how does that modify our equations finally? Remember all the equations we used before for the colligative properties? The four equations? This is how these formulas are now affected by the Van 't Hoff factor. With the vapor pressure lowering, it's a little bit complicated. You can't really add the Van 't Hoff factor over here. You have to add it towards, because it actually affects only the moles of the solute. So I wrote this down here. Technically, the mole fraction of the solvent is the one that's affected. And it looks like this. So you have moles of solvent, over mole of solvent plus I times mole of solute. So that's where you see the I. So if you're going to multiply this by P of solvent, the same thing on this right, P of solvent, and you're able to figure out the new pressure of the solution when Van 't Hoff factor is operating. That means the scientists use an ionic compound for the solute versus a molecular compound. With the rest of them, I would say it's so much easier. You just multiply into it. Whatever Van 't Hoff factor is, multiply it here. So we still have the original equations that we have for freezing, changing freezing point equal, I like to write my Kf first, times M, but don't forget to include your I. So I had a student ask me this in lecture once. Hold on a second, let me. Okay. They asked me one time, so which equation do we use? Do we want to use these ones here for a calculation or use the original one or both? I told the student, I would say, like, when it was me, I used this one here in the place of the first one, right? What this one did was remind me to watch out for my formula, because when I'm trying to find what delta TF is, what KF is, what M is, I get to this one, I'm like, wait a minute. The only way to figure out I is to look at the formula provided. And if I is molecular, if the compound is molecular, I is equal to 1. If it's ionic, I have to figure out how many ions are formed, and I can adapt accordingly. You get what I'm saying? So I suggest that if you have the option of the two, use this one. Even though in default, when I'm teaching, I leave the I until we get to this bottom part here. I don't want to confuse it too soon. Okay? Same thing with delta TB. Once again, you want to, when you're working this out in the equation, include the I, so you can always kind of double check your formula to see if I is 1. I is 1, remember, when you have non-electrolyte or molecular. Ooh, come on, arrow. I pressed the up arrow by mistake. Molecular. There was all that space. Okay. And of course, for the osmotic pressure, you want to add your I there too. Don't forget the I. Okay. Now let's go ahead and practice some problems. There was one here with the vapor pressure lowering, which is still in your PowerPoint. I deleted that one. That question is so rare you would not see it. Okay. So I decided we're not going to even spend time looking at that. Okay. Our practice problem here. The freezing point of an aqueous 0.05 molar calcium chloride, ionic, right, is, I said molar, it should be molar, is negative 0.27 degrees Celsius. Oh, it is aqueous, so the solvent is water. Okay, before I read anymore, let me write down the numbers here. I know I have calcium chloride, right, as my solute. They gave me the molal, little m, as 0.050 m. They gave me the solution freezing point, temperature freezing of the solution, which is colder than water by itself, right? Negative 0.27 degrees Celsius. Oh, this is a solution. I need to write that because that's different from the solvent and that's different from the difference. Okay. So I'm right here. Solution, boiling point, freezing point is right here. What is the Van Hoff factor, I? Okay. They want you to solve for I. What is I? And oh, please notice I has no units. Okay. So this is me right here. This is just me being me. Can't we just figure out what I will be by calculating this? Just saying, okay, calcium chloride ionizes to form what? 1 calcium ion plus 2 chloride ions, right? Why not just use this to say that I will be 1 plus 2, I will be 3. So I'm thinking what they're trying to have us figure out is the experimental one, because what we get here is theoretical. Okay, so you still have to solve it. No way out. Okay. Yeah, what is the Van Hoff factor of CaCl2 at this concentration? How does it compare to the expected value? Oh, I already got the expected one, right? Theoretical, aka expected. Okay. So we're doing a freezing point depression problem, right? Because we had freezing. I need the temperature freezing. So I'm going to move this down a little bit. We're looking for I need a temperature freezing of solvent only. Since the solvent is set aqueous, then that means the solvent is water. Water freezes at 0 degrees Celsius, right? I need the Kf. What is the Kf? Let me see. I think it's 1.86, but let me verify. Wherever that table is. It seems like it was so long ago. Hold on. I can't even see. Yeah, that table seems so long ago. Table. Oh, okay. Yes, it's actually hard for me to see the table here. Oh, somebody helping me out? Thank you, guys. It's 1.8. Thank you, Holly. 1.86. I just wanted to confirm. But yeah, y'all see in the table, right? Where was I? Okay. 1.86 degrees Celsius over little m. Okay, so delta T of freezing. Remember, delta T is essentially temperature of freezing of the solvent minus temperature freezing of the solution, right? So our solvent is 0 degrees Celsius minus 0.27. Oh no, thank you. Sorry. Yeah, okay, right there. Degrees Celsius, okay? So it's 0 degrees minus 0.27. So remember, I was telling you last time that just in case you're not sure if you're subtracting, if you have the right thing on the left and on the right, your difference has to always be positive. So 0 minus 0.27 gives us a 0.27 degrees difference, okay, delta TF. Now we can write the equation. Our equation is delta TF, the one I just got here, equal, you can add I first, KF times little m. So they want us to solve for I. We're trying to solve for this. I have delta TF, I have KF, finally confirmed it, and they gave me little m, right? So all I can do right now, I can rearrange this to get I by itself, divide by KF, and then m, right? Divide by KF and m on the bottom. This and this cancels out. I need more space. So I end up with delta TF over Kf times M being equal to I. Okay. Now, Delta TF, all we said was 0.27 degrees Celsius. So I got this part. Where's my Kf? 1.86 degrees Celsius over times. What was M again? I've already forgotten what M was. 0.050. 050 M. Okay. This question isn't really that bad. M and N cancel out. Degrees cancel out. Remember, I has no units, so that makes me feel a little confident about what. Okay, let's see. Our math part. 0.27 divided by 1.86 divided by 0.05. And we end up with, oh, an I of 2.9, like they get in experiments. So the I is not perfect, right? It's close to the one we're supposed to have, but it's not exactly the one we're supposed to have. You could do a percent error when you're comparing your results versus what they have. And so let's see. Ideally, or the expected one should be 3, the theoretical one. The one we actually got is 2.9, experimental one. Let me see how they wrap this up. They work it out. It should be 3 because of calcium chloride. Yeah, they get 2.9. So it's close, right? So as far as this is concerned, oh my goodness, we are actually done, because you can do it for practice one for iron chloride. But other than that, look at that, guys. Blank page means we're done. So what do we do with this time? Do we want to start the next chapter? Do you guys have any questions? Oh, come on. Really? Okay, fine. I don't even have the next chapter downloaded, so I have to download it, upload it, the whole process. Okay. But does anybody have any question over the whole topic? I don't think it's really a bad topic. Some people hate that part, and I'm like, you need to get yourself right in the middle of all of this. That's my advice. I mean, I can't say it works for everybody else. For me, it worked for me. But it's not a bad chapter. Just make sure you go over once again the math, the formula, understand the concepts. Highlight when you're going over the questions the important parts, right? The little tricks and things they tell you in the questions as you're going over the homework. You can tell if you get a question wrong, you want to know why you got it wrong. Did you misunderstand it? Was it something you didn't notice, maybe a word or something? And usually that will the way they write in the homework, even the PowerPoint, is similar to the way they write on the exam. So you want to be aware of the trickery, right? They call it chemistry for a reason. At some point when I was in grad school, I'm like, this is a whole mystery. It's a mystery. Okay. So you kind of want to really pay attention like an investigator while you're solving problems. But yeah, guys, this is all I have. I mean, I'm not used to being early, so I'm like ramble on. But so no questions for real. Homework is good. Quiz is good. Lab is good. Everything is okay, I'm assuming. I mean, if it's good, I'm actually going to let you guys go early. I mean, what am I going to do with myself for 25 whole minutes? I'll be fine. I'll work on something. Yeah, so the exam is available for you to start working on. When is your exam due? Is it this weekend? I haven't really been, because oh, Sunday. Okay, well, I'll let you guys, yeah, I'll let you guys. If you do have any additional questions during the week, just email me. If I'm by the computer, being that it's going to be so cold outside, I probably might be at home a little bit more. I still do go out and do stuff. So if I'm not by the computer, I'll let you guys know. And then whenever I can get to the computer, I can respond to you. Okay. But yeah, this is all I have for today. So y'all have a nice day. I'll talk to you, I guess, next week. Okay. Have a nice weekend. Bye. You're welcome, Sam.